we're going to do this. Euclidean mirrors. Somebody once told me, a student from many years ago, because I thought I don't care about the experimental results so much, I care about the theorems. And the student said, actually, I don't think that's exactly right. What you care about is the methodology. And I think that, the way things work and how come they work and why they work. And the theorem is only useful for me, mostly useful to the extent that it illustrates what you might want to do. And real data, if you will, is useful in giving examples of when it works and when it doesn't work and things like that. And so to some extent, I want to talk about Euclidean mirrors here as a methodology for dealing with time series of networks. And so it's almost the end of the conference, and so let's just do pretty pictures, mostly. And so these pictures, on the left I have the estimated mirror, and on the right I have something I call the isomirror, and I, to some extent, will tell you what those things are, but right now they're just dots. And what I have is a time series of networks, maybe 100,000 vertices per network. It's monthly in this case. I have it better for a large organization that might be Microsoft, but might not. And so I have monthly time series of networks, and the vertices change a little bit over time, but I do know which vertex, when that vertex is in the entire thing, I know which vertex is which across time. And so I have 24 by 100,000 matrices. Who talks to whom during that month? They're weighted. How often do they talk during that month? They're directed, et cetera, complicated data set. And each dot in this plot is a network. The network in January of 2019, et cetera. And where they come from is this estimating this Euclidean mirror. But in this particular case, when we just make this plot, whatever it is, it turns out that I'm going to have 24 dots because I have 24 networks. If we look at it, you might not be able to read it, but you can believe me and look at the color. It turns out to go from January of 2019 pretty much following time as we go like that. It wouldn't have had to do that. But the network time series itself has some structure, and we're capturing that that there's this seemingly like curve in R2 that is explaining something about this entire network time series. And so the curve that we don't see, but we're positing, would be the mirror for this network time series, and then these dots are the discrete estimates of the mirror. Well, I've got this very complicated data point, 24 times 100,000. And it's looking like a curve in some low-dimensional Euclidean space, or it's trying to be a curve in low-dimensional Euclidean space, and that's pretty nice. But doing inference on curves in low-dimensional Euclidean space is a little bit tricky. And one thing you can do is, if you posit that there is this curve and time follows the curve, you can look at the geodesic distances along that curve as an object, and so we can estimate the geodesic distances with something like isomap, and that's what we have over here. And so time on the x-axis, and we're looking at the geodesic distances as it change, and the one thing that we see in both of these figures is that somehow or another the change point, or the structural change for this data set happens. There's a huge change that happens right when the pandemic happens. And so we can clearly see with this complicated data, extract that kind of information. Another story. This is brain organoids. And so they're growing brains in a dish, the neuroscientists, and for these particular people who are caring about understanding autism or something like that. No, autism, something about autism. And so the brain is growing, and so I get this collection of networks again across time, just like before. Now there is no one-to-one correspondence because as the brain grows, the number of neurons and everything changes. And so we have to do some graph matching across time, kind of related to Aries talk. But my objective function is different than Aries in the Flywire challenge because my goal is the subsequent inference of finding structure in this time series of networks. And so that's why I'm doing the graph matching. But that's done, and we look at this, and we, again, each dot is a network. That is this brain organoid measured at time t. And we might see that it's piecewise linear with a change point at day 155 or whatever it is. And so we report that to the neuroscientists, and they go back and they say, just like the pandemic hit, they say, oh, day 6 months or whatever it is when neurons distinguish themselves between excitatory and inhibitory. And so we don't know causally if that's what's causing the change point, but there is a fundamental change in this brain organoid in this time series of networks at precisely this time. And then the third story, an LLM story, which, like the other two, is a long story, but I have a time series of interacting large language models, and don't want to go into it in too much detail, but they ask each other questions over time and choose someone to ask amongst the other LLMs and update their RAG databases, vector database, and go on. And I can control this, and I have two versions here, the red one and the blue one. And the red one is just this process by which they communicate and update themselves is stationary. And the red isomer is stationary. And then the blue one, which might be green, at time 20 or something like that, we induce an exogenous change in the process by which they communicate with each other. And now when I look at the time series of networks, the isomer clearly sees that change. So 3 stories, all of them incomplete from your perspective, but I understand all 3 of my stories, and I like them, and you can read about them. But they all show that particular type of structure change in a dynamic network can be captured by this mirror idea, says me. Okay, and so Avanti, Zach Youngzer wrote this paper, which is brand new in the Journal of the American Statistical Association, which you won't have heard about being machine learning kids, but dinosaur statisticians read it all the time, like cover to cover every month, in hard copy. So we consider a dynamic network model. Each vertex in the network has an associated time-varying, low-dimensional, latent vector of feature data, and the connection probabilities are functions of these latent positions. So that's a pretty yellow sentence, but it's a standard thing to do if you want to do inference using eigendecompositions, and by God, do I want to do inference using eigendecompositions. So that's what we just go ahead and assume. Under some assumptions, the evolution of the latent vectors exhibits this low-dimensional manifold structure when measured under a suitable distance. And so that is going to be our fundamental assumption that gives rise to this curves in low-dimensional Euclidean space. The distance is looking at only the observed or approximated by looking at the observed data. So we've got a statistical function a theoretical function, and now we're going to estimate it with real data, and we can do that. And that's going to be the Euclidean mirrors, this low-dimensional thing, and so we can do things like find structural changes in the network. So that's the story. And you can read all about it, and I will show a couple of results from there, but I won't do justice to them. So there's a time series of networks with a change point. The networks can be weighted, directed, colors on the vertices, colors on the edges, it doesn't matter. The difference between a change point and an anomaly, just for completeness, because it comes up a lot, is if the change in the network structure happened at time t star and then I went back to what it was like before, that would be an anomaly, and a change point would be the change stays. And so now a reasonable question is whether the pandemic thing in the organizational mirror was an anomaly or a change point, but that's not that. Okay, so this is just for expository reasons. I get to say a couple of things. So the latent position process has some properties, and one of them is that it's Euclidean realizable. So this is, under some assumptions, this process that's governing these underlying latent positions can have a one-dimensional mirror. So the mirror throughout will be psi. In the figures, the dots were psi hats, estimates of the mirror, and I was arguing that it looked like there might be a curve, a nice smooth curve there, so that curve that wasn't there is a psi, and as long as that curve is nice, like Helder continuous, then when I estimate them according to the algorithm that I haven't shown you, I get psi hats that have a particular property. And now, just so that you don't think to yourself you know what's going on, I have psi hat tildes. So whatever is going on, it's way beyond explaining to this audience, but that's okay. I'm observing the networks at discrete times, and then there's some linear algebra and some eigendecompositions. But at the end, I get estimates psi hat tilde of the true mirror psi, and the worst case over all time is bounded above by something. Well, first of all, there's a Helder continuity property, but there's also this rho, and it's not going away. And rho is basically how fine the time points are. So, I mean, if I'm only observing at discrete times, then I can't get an estimate for the points in between those discrete times that disappears without letting that just shrink. But the important or the interesting thing to me is this thing on the right, and I have m log n over root n times something. So m is the number of graphs in my time series of graphs, and n is the number of vertices. So if we fix m, for instance, and we let n go to infinity, this part disappears. But this part won't disappear unless m increases in some sort of infill asymptotics perspective. So the idea is if I'm estimating this curve, I kind of would expect something like this. And I got something like this. And then the second result is about, well, I talk about change points because there's a lot of ways to ask questions about finding structure in a complicated data point. A single data point is this time series of networks. But one thing you could ask for is a change point. And so if I have the mirror psi is piecewise linear, now I'm estimating psi hat, and I'm asking, can I estimate the change point, t star? And the answer is yes. And again, I have m log n in the numerator and a root n in the denominator, so that goes to 0 as n increases. This thing has an m in it as well. This is the essentially the eigenvalues of something, and then there's something to do with the discreteness of the time that I've got. So the idea, and it's only an idea here in the papers, is that as the number of vertices go to infinity, I should be getting better estimates of my mirror and of the structure, in this case the change point, and the relationship to the number of graphs in my time series is more complicated, and we talk about it a lot. I don't want to talk about it now because asymptotics as m goes to infinity, if I'm getting more and more, if time is going to infinity, is not really the interesting one to me. It's more the asymptotics in infill asymptotics that I'm getting a finer and finer analysis, but my dependent structure changes, and so you can understand that that's a more complicated story that we do tell, but not today. In any event, Avanti and Zach and Youngzer, and then the PhD student Tin Yi, who will graduate. He's hopefully when the economy comes back, when there's jobs. I don't see any reason for him to graduate when there are no jobs, but we'll see about that. But he's really good, by the way. Tin Yi is really good. I recommend him to you. So I'm not going to go into this other than the method to estimate the isomirror is to do spectral embeddings, and another spectral embedding. And long story, I'll tell you later. I want to get to something else. But the idea is you just stack eigendecompositions on top of each other. And if I have another dimension in my problem, which is, say, multiple time series of networks, I'll just do another eigendecomposition someplace and just keep doing eigendecompositions. And that's what I do. But the algorithm that I have is you can have the code, but in some sense it's just glorified stacking eigendecompositions. Now I do want to spend a couple minutes on this because this is the basic theory in this JAZA paper. And on the right we have the truth that we don't observe, and on the left we have the way we estimate it. And so phi here is the latent position process, the underlying stochastic process governing the latent positions. And there's a distance on latent position process at time t and t prime, which is this, broke your screen, which is this, let's say, quasi-covariance kind of operator if you look at it. So I have the latent positions at time t minus time t prime, but I have to do an orthogonal transformation because of inner product behavior, non-identifiability. I do that, square it, and that's my distance function. Well, I can estimate that by taking the adjacency spectral embedding of each graph at each time, and then I have to, again, find the orthogonal transformation that best matches those, and I'll get my estimate of this true distance. Well, the mirror shows up right here as a finite sample mirror of the psi, of the phi, I'm sorry. So psi is the mirror of phi. Phi is the latent position process. Psi is the finite sample thing that's trying to be like that. And I build that into this distance matrix. And the distances between, at I and j, between the phi look like the distances at I and j between the psi, the mirror. And then you take a multidimensional scaling of this distance matrix, gets me to low-dimensional Euclidean space, and that's where my psi lives, and I can do the same thing with my estimated thing here. I can estimate this, and theorems 6 and 7 in the paper say that this estimate as n and m and whatnot goes to infinity. The left-hand side looks like the right-hand side, so I can consistently estimate that mirror, in which case I can consistently do subsequent inference, finding structure changes and things like that. So there's our story. Yes, I can find useful geometric structure via as the statistical inference for such a story. And then bunch of stuff that I'm not going to say because Teresa gave me a half hour instead of 3 hours, which I demanded. So you all owe Teresa a favor. But I want to say something here. So the mirror, the theorems were if the mirror was, say, one-dimensional, and there was no need then for that last eigendecomposition, which is, say, manifold learning, finding the isomap or something like that. But if the mirror is d-dimensional, then I've got a whole bunch, if I have a bunch of time series of networks, let's say, then I have a whole bunch of one-dimensional curves winding through d-dimensional space. And if I want to do something on them, cluster them or do ANOVA, since that's what dinosaur statisticians do is ANOVA. I mean, what else are you going to do? That's complicated. A bunch of one. And so instead I do isomap to one dimension, then I get this thing, lost some information, but I know how to deal with it. So that's what I call the D to 1 isomer. And so I want to tell, and so that's a really great thing, I want to tell in my remaining 3 minutes another LLM story. So my Microsoft research people, unlike Jacqueline's, have come up with this thing called lazy graph rag, and some of you know a whole bunch more about LLMs than I do, and rag and vector rag, and then Microsoft and some people came up with this thing called graph rag, which is better than rag when it's better than rag. And then, but it's very computationally intensive, and so you have lazy graph rag, which is less computationally intensive and got nothing to do with time series of networks, perhaps, except a bunch of LaTeX takes a collection of models, a collection of queries. I do IID replicates for each query, each model at each query, and I do linear algebra that turns out to be a bunch like what we did for networks. So when does a dinosaur statistician work on LLMs? When it's the same linear algebra. That's the chicken and crossing the road story. And so at the end of this whole thing, I have multidimensional scaling get me down to something that I do call psi hat because it's playing the role of the estimated mirror, but now it's in LLM world. And still the question is, what's playing the role of time? And there's a couple of different cases. In one case, I had time series of interacting LLMs, so there it was really clear. But here, time is playing or budget is playing the role of time. So in the Euclidean mirror story, time isn't necessarily what you think of as time. It's just any ordered index for my networks. And time is sort of the obvious one, but it wouldn't have to be that. Well, now I have a bunch of LLMs, if you will, which are lazy graph rags built for a different budget. The ordered index is budget. And for each of 4 different categories of queries, this particular LLM can be, I can turn it into this mirror-like thing, this estimated mirror, via some linear algebra, much like what I have shown you, but not exactly. And if I do this for 4 different categories of queries, I find that, and now I'm not looking for change points, I'm just asking if the slope is 0 or not 0, which is a wonderful statistics question, h naught beta equals 0. And it turns out that in 2 of these cases, I don't reject the null hypothesis, very strongly don't reject the null hypothesis. And in the other 2 cases, I clearly do have a slope, and I have a slope where the lazy graph rag with a low budget is a long ways from the full graph rag, which might be thought of as the goal. But as I increase the budget, I decrease my distance in mirror space anyway to this idealized kind of thing that's a graph rag. And for these, that's for global questions, that is questions for which the relationship between objects would be valuable. Because vector rag it has a hard time capturing that, and that's the whole point of the graph rag. So in these local questions where that shouldn't matter much, we don't have any slope whatsoever. And so these results make sense, and they're showing the way to use these Euclidean mirrors for LLM story. So my time is up, so let's end with that. And I want to say again, the linear algebra theorems for their own sake isn't the point. The results on any particular real data set isn't the point. But I do believe that for kids today, the idea that there's a bunch of mathematics anyone can do, and there's no shame in doing mathematics that somebody could care about. And so if you hang out with people like Teresa or scientists, LLM people or neuroscientists or whoever's got the data, and you try to come up with methodologies that are potentially of value, that's one way to build a career. Thank you.
That there's different ways to think about time. Have you looked at kind of what happens in learning dynamics, whether there are change points in learning dynamics of a neural network, and whether you can detect that using your methods?
Yes. What do you call it? I'm an LLM expert when I talk to my people. But checkpoints? Yeah. Model checkpoints. And so you look at this with Amazon, we did that, and we're still doing that. And we're looking at various checkpoints and asking, can we make some sort of prediction about whether it's worth going beyond a particular point? And you see very much like this, the mirror has a pretty clear change point. And then the question is, in hindsight or with the evaluation, does this change point correlate with performance? And the answer was yes, and so they're happy.
So I'm a little bit confused. What is mathematically what you call the mirror?
Uh-huh.
What is it? It's a function that, given a graph, returns a real value?
No, it's a function. The mirror is a function on latent positions. So latent positions, I have...
the nodes. So the latent positions are one per node.
One d-dimensional latent position per node. So the latent position matrix will be an n by d matrix at each time t. And that matrix can evolve across time however you want. But if you put a stochastic process that governs the changes, the evolution of the latent position matrix across time, then that's the latent position process that I call phi. And then psi is the finite dimensional Euclidean representation of that as seen through this distance matrix that I called d sub mv, which was like a quasi-covariance operator. So you define a distance function on the latent position process at times t and t prime, and then you ask about representing that distance function in Euclidean space, and that's the mirror. Exactly.